All right, welcome back to physics. So we're going to take a look at deriving the electrical field for for any point around or inside a sphere. So again, we're going to use Gauss's law. It's really handy for this. It has a nice shape. So if I see something like a sphere, I want to be thinking about Gauss's law. So brief reminder, so Gauss's law deals with flux, and it tells us that the amount of flux can be calculated two different ways. One way is we can have the product of the electrical field times the area. This is a dot product, so they have to be in the same direction. And that gives me a value for the amount of flux. And I can also calculate flux using Gauss's law, which formally says that the enclosed charge divided by some constant will tell me the amount of flux that's there. So importantly, what I'm going to try to do is I'm going to try to come up with some surface that's going to capture all of the flux, and I can use the area of that surface to figure out the electrical field. And then I need to figure out the charge that's enclosed. So notice I'm trying to set up so E is constant, and of course epsilon naught is a constant, so I'm trying to set up, I have to figure out the area and the charge that's enclosed. So let's take a sphere. I'm going to have some sphere. It's going to have some charge. Let's look outside the sphere first. So as always, I'm going to give this some radius. That's not changing. What I'm interested at some point out here, say, I don't know, here, and the distance here, I'm going to call this lowercase r. And so my lowercase r, I can change. I want to find a value for an electrical field on that r. I'm expecting this is going to be the same as a point charge, so I should end up with electric field being inversely proportional to the square of the radius. So I think I'm going to end up with E is going to be my constant, 1 over 4 pi epsilon naught, times the charge over r squared. So I think I'm going to get there. That's where I think I'm getting the end. So let me check, see if I can do that. So how am I going to do this? Well, I'm going to have my Gaussian surface. So I'm going to set up a sphere, and everywhere I look on the sphere, I'm going to have the same electrical field magnitude and technically the direction going away from the center. So if I look here, I get one electric field. I look here, I get the same. So this is really important because this allows my electrical field to be constant, and then it has to, that greatly simplifies the math, so that I can pull E out of the integral. Right, so I set up a consistent shape that allows the electrical field to be the same everywhere on that two-dimensional surface. Right, so then when I add up, so I'm going to set my flux equal to the closed surface integral of E dot dA. So my surface has a vector. It's going to be pointing away from the center, and my electrical field line is going to be pointing away from the center. So those two are going to be lined up, so the dot product takes care of itself. If my electrical field is constant, I'm going to pull that out. So I need to figure out what is the area of my Gaussian surface. So this is a sphere. An area of a sphere, the surface area of the sphere is 4 pi r squared. So I can have one expression for flux, which is going to be my electrical field, times the area that I'm interested in. So all of that flux must go through that area. The second part of this we want to set it equal to is Gauss's law, which says that this is some whatever charge is enclosed divided by the square of by epsilon naught. Right? So let's see how this works, right? So the charge is enclosed. So all of this is enclosed. So whatever charge I have here, I'm going to give this capital Q. Whatever charge I have there is fully enclosed. It doesn't matter if it's here, 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 or here. We're talking about flux, right? So flux, importantly, flux. So it doesn't matter where the charge is. It could be anywhere. And so I'm going to end up with Q, capital Q, over epsilon naught. Now I'm going to set these two equal to each other. So I'm going to have E times 4 pi r squared. It's going to be equal to Q over epsilon naught. I'm going to rearrange this for E, and I'm going to get Q over r squared times 1 over 4 pi epsilon naught. So that's what I was hoping to get to, right? So, so that's consistent. So I got the same thing. So outside of my sphere, if I was to plot this, here's my radius r. So if I plot my distance here, my electrical field going from the center here, I don't know, I'll figure that out. But outside of the surface of the sphere, it's going to drop off with the square of the radius. Oops, well, imagine that doesn't go to 0. Anyway, so we'll look inside the radius next, so hang on for that.